Everyone, welcome to a quick review of our lesson 1.10 structure and meaning in our algebra unit. I wanted to go over a few things before we get into the examples. So a lot of times you're going to see real world examples with different expressions. So here's an example I'll write on the board. 25x plus 50. Now remember, we learned that this number here, usually at the end, it's the number that does not have any variables with it. Remember, that's called the constant. It's never going to change. It will always stay that value, right? Because there's no variable with it. In this example, it's always going to be 50. This term over here, 25 times x, this one is going to change. It's going to vary because it does have the variable with it. So depending on what x is going to change the value of this whole term. So that's the first thing we want to keep in mind. So anytime you're dealing with a real world example and you're given an expression like this, you want to think, okay, well, what's not changing? And we'll see some of those examples. One that comes to mind is when you open a bank account and you have to give the bank an amount of money to open it to start with. So a lot of times this constant value is your starting value. So let's say I went to the bank, I opened an account, and I had to give them $50 to open it. So I started with $50, and then every month my balance will vary. So in this case, maybe we're saying that there's an interest rate of 0.25, I could add a decimal there, and depending on how much money I put in the bank, so X being the amount of money in this example, is going to change the total balance of my account. So that's just one example. We'll see a few where the constant value will mean one thing, and then of course this other term here will mean another. And then the entire thing also has another meaning itself. Usually it means total, right? When you see that plus, you're adding two things together to get a total value. So we're going to see different examples of those as we go through this lesson. Oh, something else I wanted to show you guys before we go on. Let me get a different color here. We're going to see a lot dealing with money and discounts. And so whenever you see something like 50% off, you might see that in clothing stores a lot, or maybe at Best Buy if you're going to buy a computer. Whenever we're dealing with percent off, the way you find a percent off is you're going to multiply the cost of the item by the percent. So we would usually see costs of the item in dollars, right? So let's say an example here, $300. Let's say our $300 TV is 50% off. Now we always want to multiply the value by a percent because there's no what do you call it? I'm sorry, not a percent. There's no percent button on the calculator. So we want to always multiply by a decimal. I misspoke earlier. It's not a percent. You want to multiply by a decimal. So we want to turn the percent into a decimal. So I wrote 50% as 0.5. Well, that's a weird pointer. Let's get the pen back. Okay, so to remember to do that, all you do is you move the decimal 2 places to the left. Now, you're not actually going to have to change percent to decimals in this class or in this unit at all. I just kind of wanted you to see that a percent off translates to a decimal multiplied by the total in these examples. So you might see something like this. 0.5 times 300 minus, I don't know, I'm just making this up now, 5. So you have the cost of the TV, and maybe there's a coupon. So you're subtracting out the $5 coupon first, and then you're multiplying by the discount. This is just an example. Ooh, we could even add on multiplying by a tax. So most things you buy here in the state of Virginia do have a tax rate of 7 or 7.5%. So I converted that percent to a decimal. Again, remember, you do not have to convert percents to decimals. I'm just showing you how in the expressions we're going to look at, you're going to see these decimals, and those are basically the percents converted. So whenever you see you're multiplying by a decimal, it's you're doing a percent off or you're multiplying by a tax rate to change that value of the whole expression. So let's look at some. Here's the first one. The expression 2x plus 50, so this looks familiar, right? We have two terms. The first term has a variable with it. The second term does not. So we already know that this is the constant value. So all we have to do is look and see what, let's put it in context of the problem. It says that it represents the elevation above sea level in meters of a rock climber after X minutes of climbing. What is the rock climber's initial height above sea level? So this entire expression represents how high above sea level a climber is. So depending on how many minutes they've climbed, see X is the number of minutes, it's going to change how high they are above the sea level, right? That makes sense. If you're climbing up a wall and you've been climbing for a minute, you get a little further. Let's say you climb for 20 minutes. You're obviously higher. So your height is going to change based on how long you've been climbing. And that makes sense. If you're climbing up, I'm going to pretend like we're walking, but if you're climbing up a mountain or up a rock, the time lapsed, of course, is going to depend on how high you've gone up. Unless you've fallen, but hopefully you haven't fallen, right? Let's make a mountain here. Okay, so it says, what is the initial height? So there's a few ways to think about this. When you think of the word initial, it's the starting point. So how many minutes have passed if we've just started? And that's no minutes, right? None. So we could let x equal 0 because no minutes have passed. That's our initial time. So let's plug in 0 for x and see what our height is. And it is 50 meters. Remember, it said it was in meters. So we are 50 meters above sea level at the beginning. So maybe there's like a ledge here, you know, and the sea is down here. So we're already 50 feet above sea level when we've just begun. So you can certainly plug in 0 minutes for x because that initiates the initial height. Another way to look at this is the 50 is the starting point. Remember we talked about that with the bank account. This constant value here is always going to be your starting point, whether you're talking about money or climbing a mountain. So the answer is 50 meters. Let's look at number 2. The final cost of a bookstore purchase with a $5 coupon in a state that charges an 8% sales tax is given by this expression. The variable x represents the amount of the purchase before the sales tax and coupon are applied. So x is the amount of purchase. X is the amount of purchase, or the cost of the item, before anything happens. So you can think of this as like the ticket price. You know, you're shopping, you see a sweater, you look at the ticket. That's x in this example. And then there's a $5 coupon. So you can already kind of see in that expression that the $5 coupon is represented by the -5. It's really the only one that makes sense, right? There's no other 5 there. And when you're talking about a coupon, remember that should hopefully trigger in your brain subtraction, because with a coupon, you're getting that discount, that $5 off. So all of those words sort of signal us to think of subtraction. Subtraction. So we're going to subtract that $5 coupon. The last thing to look here is the 8% sales tax. So remember we talked about turning percents into decimals. You don't actually have to do that. The expression itself is already done for you. You can see there's that decimal of 0.08. Now it does have a 1 in front of it, and this example is showing when you multiply it by the whole thing. So they did like basically 108% of the price. So it wants to know, what does the x minus 5 represent? So we're basically sort of just turning this numerical expression into meaning. We're giving it meaning in this context of this problem. So remember, the x represents the ticket price of the item, and the 5 represents the coupon. So when you take x and you subtract 5 from it, I mean, we could use a few different ways to describe this here. I would probably just say it's the cost. You could say it's the cost after the coupon, right? Because we subtracted that coupon. Another way to sort of think about this is you could say it's the cost before the tax is applied. Before the tax is applied. So there's definitely a few different sort of perspectives for this one. And I know that most of our questions in our quizzes and tests are multiple choice. So you'll definitely just want to pick the one that makes the most sense. It's going to be either, I didn't look at the answers for this one. It's going to be either the cost after the coupon or the cost before the tax. Just again, depends on your perspective. If you're subtracting the 5, you've taken the coupon off. So there it is, the cost after the coupon. Or if you're just talking about this parentheses, we have not yet multiplied it by 1.08. So it is the cost before the tax. All right, let's look at number 3. They give us an expression, 0.09x plus x minus 30, and it tells us this expression is a model. It's the final price of a bicycle with an instant rebate. So hopefully these two words here, instant rebate, triggers something again in your mind to think subtraction. So we're going to subtract out. A rebate means you get money back. So we're subtracting out a value. And there is sales tax. So remember, tax is always written as a percent that we have converted to a decimal, or the problem has converted to a decimal for us. So I would go straight to the decimal, and here it is. There's the decimal, so we know that's the tax. Here's the money off, right? The minus something. That's the rebate. And then we have some x's. Let's see what x is. I don't know that it necessarily tells us here. Let's see. The tax, okay, the tax is on the original price. There we go. So the tax is being multiplied by x. So x is the original price. Doesn't explicitly say, let x equal the original price. What it does tell you, it says the tax is on the original price. So we need to sort of put those pieces together. We know that a tax is a decimal, so the original price must be x in this example. Which expression represents the amount of tax that is paid on the bicycle? Well, remember, we're buying the bicycle, so the price of the bicycle is going to be x, and there's that decimal being multiplied by the price of the bicycle. So this is going to represent 0.09x is the part of the expression that represents the amount of tax that is paid on the bicycle. So it looks like in this example, they are taxing the price before taking the rebate. See that? It's totally separate. They're going to charge you tax on the entire original price, and then they're going to add in whatever's left once you have the rebate from the original price. So that's interesting. Usually, I guess because a rebate is after the fact. So, if you think about, you guys may never have gotten a rebate in a store before, but you do submit it in after you've purchased the item. It's not like although this one says instant rebate. That's interesting. It definitely doesn't change the answer to this problem because we're talking about the amount of tax. But in this expression, they're definitely charging tax on the entire price of the item before the rebate, because you see the rebate part here is in this second part of that expression. So that's just interesting to me. All right, number 4, some friends decided to equally split the cost of gas on their trip. Equally split. Here's the expression, 3G over 4. And that represents how much money each person had to pay in dollars for G gallons of gas. Ooh, so they tell us that G stands for the gallons of gas. And this entire expression is going to give you guys the cost per person. Per person. So how many people are on the trip if it's the cost per person? Okay, so it pretty much just kind of said the answer out loud. Let me get my pointer back. So this represents the cost per person. So that's it. The cost is on the top per person. So whenever you have a fraction, just like we were doing in our dimensional analysis, remember inches to feet, things like that. So the cost is on top and the number of people is on the bottom. So it says, what does the expression 3G represent? It represents the cost. The cost before, we can just say the total cost, but it's the cost before splitting it between 4 people. There are 4 people. Because remember, that's when we divide by 4, we're dividing it into 4 equal groups for each person to have their equal share of pay for the gas. So the answer is total cost. It's a total cost before dividing it amongst the group. All right, this will be the last one. The expression 625 times the quantity 1 minus x gives the discounted price of a television. So you're taking 625 times 1 minus x. It tells you x is the percent of the discount, and that kind of makes sense, right? Because discount, you think of subtraction. And we always write percents in decimal form. So in this example, they don't give you a percent to deal with in the expression because the percent is the variable. So this is actually kind of a really good working expression, especially for consumers like you or your parents or your learning coaches or your neighbors, people who go shopping at the store. You guys could have an expression like this and then compare prices. It's also good for businesses if they want to say, well, what if we, gave 20% off on TVs today? What would our prices be? Or what if we gave 30% off or 40% off? They could easily and very quickly just insert those decimal percents and get an output, get a total cost for their TV. So this is really cool. I like this working expression kind of better than the other ones because you can vary the discount. That's what is being represented by the variable, the discount. So it wants to know, what does the 625 represent in this equation? And anytime you're multiplying a discount by a number, that's going to be the cost. So this is the cost of the television before the discount. Cost of the TV before the discount. So you can see problems in this unit involve very little to no actual math computation. It's all about problem solving and critical thinking, reading the words and taking those words and translating them to math symbols and math ideas. So when you think of things like discount, remember that means subtraction. So those are all clues that are going to help you answer these questions.